Okay, good morning. Really pleased to see so many of you here at this somewhat early hour. My name is Will Oliver. I'm a professor in electrical engineering and computer science. That's my home department. I'm also with professor of physics. And I'm really pleased to organize this day where we're going to talk about quantum computing. And before we get started, just want to thank the College of Computing, the MIT Schwarzman College of Computing, for organizing not just today's event, but the whole week. Many of you may have come for the events earlier this week, and it's really fantastic that we do this during IAP. Today is focused on quantum computing. I'm going to start it off with an intro to quantum computing. Some of this is related to a course that we teach online through MIT X Pro, which both myself and Ike Chuang, who is our second speaker, put together a few years ago. It's been quite successful. If you'd like to learn more about quantum and you have a few weeks, let me know, because this is a great way to continue what we're going to talk about today through the MIT X Pro platform. So this morning is going to be an intro to quantum computing. I'll speak, and then Professor Ike Chuang will speak also for an hour. We'll break for lunch. And then this afternoon, we have some more focused topics, including different quantum computing platforms, and also, state-of-the-art or cutting-edge research. Where are we today? And it will include both quantum computing, but also security. So Professor Vinod Vaikunathan will talk about how do we mitigate or combat the threat that quantum computers pose to us. That's his expertise. Professor Aram Hara will talk about algorithms. Yelena Notaros will talk about integrated photonics. And then Kevin O'Brien, I see that the list here is, okay, never mind. The titles are on the top. Yeah, so Aram will talk about quantum algorithms. Yelena will talk about integrated photonics for trapped ions. And then Kevin O'Brien will talk about electronic circuits that behave quantum mechanically. We'll take a short break then, and after that we'll have a panel discussion, but really what I'd like to do with that panel discussion is really open it up to questions and have it be a free-flow Q&A. So with that, if there are no questions, why don't we get started? Good, so I'm going to start it off with quantum engineering of superconducting qubits, or quantum computing more generally. We often call quantum computing quantum 2.0. Why do we call it 2.0? Well, there was a 1.0. What you see here is a picture from the Solvay conference in 1927. You probably recognize a lot of these folks. Many of them won Nobel Prizes. Either they had already won it or they were about to. In fact, one person here, Madame Marie Curie, won it twice. This is what we call the first quantum revolution, quantum 1.0. It's when we first understood that nature around us is not classical. It's fundamentally quantum mechanical. And in certain limits, it behaves classical. And that's generally what we observe. Now, based on that, we were able to develop several technologies which are manifestly classical, but we could not have understood them without quantum mechanics as a foundation. And I'd like to start here, I guess I'm an electrical engineer, so I would like to start here with a history of classical electronic computing. How did we get to these fantastic computers we have today? Well, it took well over 100 years of development. We started with the vacuum tube. That was 1906, three-terminal device. It was used for radio transceivers for almost 4 decades, 40 years, before it found its use in a computer called ENIAC, developed at the University of Pennsylvania, a vacuum tube-based computer. Of course, to get closer to where we are today, we needed the transistor. That's Bell Labs in 47. And by the mid-50s, we had fully transistor-based computers, this one called TX0 or TIXO. But it didn't look like the computers we have today in the sense that those transistors were basically soldered together. Okay, and the memory was completely different, a magnetic core type memory. To get closer even still to where we are, we needed integrated circuits. That was the late 50s in germanium and then in silicon. And of course, it wasn't until the 70s that we finally saw something that you would look at and say, oh yeah, that's an integrated circuit. That's a chip. This is the Intel 4004, a 4-bit processor with only 2,000 transistors. Revolutionary at the time. To get closer still, I remember using Pentium Pros in the mid-90s, millions of transistors on a single chip. That was fantastic. But remember, that was already 30 years ago. And here we are today with wonderful computers, GPUs, CPUs, XPUs, all kinds of processing units, 3D integrated, right? And the system on the chip now has 100 billion transistors. And that's fantastic. And these computers today are amazing. But we can't forget that those amazing computers, their progeny is well over 100 years old. Okay. And why do I talk about this in so much detail? Well, because quantum computing is nascent. In the 80s, people like Richard Feynman said, look, if you want to simulate or emulate a quantum system, you should use another quantum system to do it, because it's really hard on classical computers to keep track of all of those degrees of freedom. That was true in the 80s, still true today. Now, people thought about this, and it wasn't until maybe 15 years later that we started to see the algorithms that one would imagine using or running on a quantum computer when we could build it. No hardware at this point. And calling out to Peter Shor and his algorithm, which attacks public key crypto systems. We'll hear a lot about that today. But of course, if that were the only application, it would not drive commercialization. We would need it, of course. We care a lot about security. But to drive commercialization, we need algorithms. We'll talk about algorithms throughout the day today. But algorithms that are commercially viable and relevant, right? People will pay money to run. And we'll talk about some of those algorithms. And many of them had their seeds in the mid-90s. And 30 years later, here we are today. We have small-scale quantum computers, maybe 100 qubits to 1,000 qubits. They're real. They work. But they're too small to be commercially viable. Usually when people think commercially viable, they're like, okay, when am I going to have a quantum computer that tells me the formula for a pharmaceutical drug or something like that? That is going to take a very large error-corrected quantum computer. And we'll talk more about that throughout the day. But the quantum computers we have today, you can run algorithms on them. They're just small. And you can prove that those algorithms work. And it also gives you insight into how large a hardware quantum computer am I waiting for this to be commercially viable. So the takeaway message here is that quantum computing is real. It's transitioning from what you might call a scientific curiosity to a technical reality that's happening right now. As engineers, we know that advancing from some fundamental discovery to a useful machine, it takes a time, it takes a lot of engineering, systems, right? We have to have that type of thinking. We're there now. The other thing is you must be in the game to play. And what I mean by that is the companies that are making these fantastic, billion-plus transistor chips, they didn't wait for somebody in 2010 to figure out how to do it and then just jump in and start producing them, right? There's a lot of trade secrets, right? This is hardware. It's hard tech, and you got to be in it from the beginning. Okay. A lot of activity going on worldwide, and I won't read through this whole chart here, but the point is that funding for quantum computing started largely with governments, driven primarily by the security concern of Shor's algorithm. But since then, I would say within the last 10 years, there's been a tremendous push towards commercialization. And this is not an exhaustive list. It's just what I could fit on the chart. And a few of these companies are trying to build quantum computers or quantum sensors. But most of them are trying to figure out how quantum's going to affect their bottom line in the future. And then some of them are the picks and the shovels that are needed to make quantum computing a reality. So this commercialization and ecosystem is happening right now. So what are qubits? Like, what is the fundamental logic element of a quantum computer? Well, they come in two flavors. One flavor is the natural atoms that we have in our periodic table of elements. You can see them here. And we know that depending on the number of protons, the number of neutrons, and the number of electrons, we form these Bohr-type atoms. And each element has different properties, depending on those numbers, okay? And some of them we can pick out and use to be our qubit. And in particular, we look for those that have energy levels such that we can call one of them 0 and one of them 1. Okay, we'll talk more detail about that. But these are the natural atoms. Another way we can do it is we can build electronic circuits. And the electronic circuits have inductors, capacitors, and Josephson junctions. And depending on their parameter values and the number of elements we have and the way that we put them together, we can form circuits that have properties that mimic or look like atoms, but of course, at the end of the day, it's just an electrical circuit. It looks like an atom in the sense that it has discretized energy levels, such as shown here. With a 0 and a 1, we can identify. And in fact, there is you could think of it as a Mendeleev table of these types of circuits, each one having different properties that we can design as electrical engineers, right? So these are the two general families of qubits. Again, we'll talk more about them in detail. Natural atoms and then synthetic or artificial atoms. Okay. So with that, let's talk about how quantum computing works. We'll then talk a little bit about superconducting qubits and engineering quantum systems. Okay, so how is a quantum computer different than a classical computer? I often use this because, of course, I was trained on classical computers. Classical computers, of course, are based on bits. Transistor, is the voltage there or not? But it could be any two-state system. The states are 0 or 1, that's it. They're discrete. Transistors are almost perfect. We've really optimized them well. And the error rate is something like 1 part in 10 to the 20. They almost never fail. If we set it in 1, we're going to measure it in 1. If we set it in 0, we'll measure it in 0. If something unfortunate happens right now, almost certainly it's the software, not the hardware. Qubits are quantum bits. We pronounce it qubit, and we spell it this way. And it's really a quantum mechanical two-level system or two-state system. And the way that we think about it is with something called the Bloch sphere, but you can think of it as the planet Earth. And if you're at the North Pole, you're in state 0, a classical state. If you're at the South Pole, you're in state 1, also a classical state. And so transistors, classical transistors, they only live at the North and the South Pole. But qubits, like people, can be anywhere on the surface of the planet Earth. And when you're anywhere other than the North or the South Pole, you're in a quantum superposition of states 0 and 1 simultaneously. Now, you can have weighting coefficients. If you're on the equator, the weighting coefficients are equal. I'm an equal superposition of 0 and 1. And if I'm away from the equator, then I'm not. I'm more weighted towards one than the other, but it is a quantum superposition, right? And this is just like you're standing at a single place on Earth. This is not a mixture of two classical states. This is a single state that has a property that has aspects of 0 and 1 simultaneously. And that's weird. All right, it's not classical superposition. One consequence is that measurement is probabilistic. If you're on the equator, let's say you go to a point on the equator, and I make a measurement, that gives me classical information out. So you need to snap immediately to the North Pole or to the South Pole. Which one? It's random. It's one of the purest forms of randomness we know, quantum mechanics, that provides us. If I go back to the same place on the Earth and I measure again, just like flipping a coin 50-50, I'm going to snap to the North Pole or to the South Pole instantly because I get that information out. Okay. So what this means is that quantum computers rely on encoding information in a fundamentally different way than classical computers do. So one consequence of this is shown here. So a classical computer with n bits, a number n bits, can form an exponentially large number of states, 2 to the nth power, but it only can represent one of them at a time. So it could be that all the transistors here are in 0, could be they're all in 1, and all permutations in between. With 3 bits, there are 8 of those, 2 to the 3rd power. And what that means is if for some reason I wanted to calculate a function with each of these as an input, I basically have 2 options. The first thing I can do is I could take one computer and then serially in time put in 0, 0, 0, get the function of that out, put in 0, 0, 1, get its function out, and I do that an exponentially large number of times. The other thing I could do is I could buy a large number of computers and I could run them as illustrated here in parallel. But either way, if I have an exponentially large number of inputs, I need either exponential time or exponential hardware to do this task. Quantum computers, you can have n qubits, and again, there will be 2 to the n components or classical states, but the quantum computer can put all of them into a single quantum superposition state with weighting coefficients. And you can think of it as this massive superposition state going into the quantum computer and then a massive superposition state coming out. We haven't measured anything yet. We didn't get any information yet, okay? Now, what happens in here, and we'll see it illustrated in a moment, is something called quantum parallelism and quantum interference. And this underpins, or is the foundation for, the power of a quantum computer. So how do we take advantage of this? So let's go into a little bit more detail to see how quantum parallelism and quantum interference work. We're going to start with this quantum two-level system. This is an electron spin in a magnetic field. And when an electron spin is in a magnetic field, it has different energy depending on whether the spin is aligned or anti-aligned with the field. Okay, so those are our two states, spin up, spin down. They have different energies. We'll call that E0, 1. Let's call spin up state 0 and spin down state 1. So again, if you're at the North Pole or the South Pole, you're in a classical state. So when this is pointed towards the North Pole here, this is just the classical 0. When we're pointed to the South Pole, that's classical 1. But we know, as we said, that anywhere other than the North Pole, we can form superposition states of 0 and 1 simultaneously with weighting coefficients alpha and beta, constrained in this way so that the unit vector is preserved. Now, just like on Earth, we have latitude and longitude. We can represent this state using phases, theta and phi, and we could write this state in this way. So at the North Pole, theta is 0. At the South Pole, theta is pi. And this is like latitude. And then the longitude is where we are along the equator. Okay. So on the equator, you could see that we are in equal superposition of 0 and 1 simultaneously, meaning the magnitude of the coefficients that sit there is equal. It's 1 over square root of 2. But we also have this phase in terms of where am I pointing on the equator. That's another phase that we have. All right. So if you have these three spins, you could just treat them classically. You could say, I'm never going to put them in superposition. I'm just going to use them as classical bits. And you could form a state register, which I just list here all the possible permutations, and from running from 0, 0, 0 to 1, 1, 1. And you could do classical computation this way. Alternatively, quantum mechanically, what we would do is we would put all of these classical states into a single superposition state psi with weighting coefficients, C1 through C8. You could write it this way. It looks more digital, but of course, we're representing it with spins. And we'll just note here that it looks like we have 8 numbers, but actually those are complex numbers. So to represent this state takes twice that number, 16. Okay. So we can now make this a quantum state register with coefficients C1 through C8. And we can now see how a computation might unfold. And it relies heavily on these two quantum mechanical phenomena called parallelism and interference. So let's just get an intuitive feel for what that is. So we're going to start with these 3 spins, and let's just focus on the first one. We're going to drive it with a pulse, and this pulse has the right area to do what's called a pi pulse. Okay, what does that mean? Well, if we're pointed towards the North Pole, a pi pulse will flip that spin to the South Pole. It rotates by an angle of pi. If the spin were pointed at the South Pole, it would rotate it back up to the North Pole, also pi, right? And so what we see is that if we were to apply this pulse onto this first spin, what we see is that we're going to shuttle the coefficients around. And let's see how that happens. So the state register before and after the pulse is shown here. For spin ups that come in with these coefficients, you can see the other 2 spins have different permutations, but these 4 portions or aspect of the superposition all have a spin up. And when we apply this pulse, we are going to flip it to spin down. And the coefficients follow along. Now instead, in that superposition state, where the spin was down, those aspects are going to flip to up, and the coefficients follow along. So what did we just do? This is amazing. We applied 1 pulse. We applied it to 1 spin, and we just shuttled 2 to the n coefficients in our state space simultaneously. Okay? That's called quantum parallelism. Now, quantum interference we can look at, and we'll now apply this pulse to the spin on atom 3. And if you notice, it's basically half of the area, which means it's only going to rotate half as far. And let me just tell you how it works. so we have before the pulse and after the pulse. If the spin is pointed at the North Pole and we rotate it around this axis pointed to the right by pi over 2, it's going to be on the equator. And I'm just going to say that that's the plus direction. Let's just say that for the moment. And what that means is a spin up is going to go to a superposition of up plus down. Equal superposition, it's on the equator, and it comes with a plus sign. Now, I'm not worried about normalization here for those who are experts in quantum mechanics. There is a normalization, but we don't need it for this illustration. Now, what happens to this spin right here that happens to be spin up with the coefficient C5? Well, it's going to go to up plus down, so it now splits between two aspects. And the coefficient C5 follows along, and it's plus for both of them. Again, without the normalization. I'm not worried about that. Now, instead, for the portion of this superposition state where the spin is down, let's just look at this one case. If you start at the South Pole and you rotate in the same direction, you'll find that you go up to the equator, but now you're pointed in the opposite side of the Earth. And so we're going to say this comes in with a minus sign. Okay. So this spin down now goes to up and down, but it comes in with a minus sign, which means the coefficient C6 follows in the same way. Plus C6 where it's up, minus C6 where it's down. And now what we see is that, for example, if C5 and C6 were equal, they need not be, but let's just presume that it's true, then for this first up, up, up portion of the state, they add together constructively. It gets bigger. And for this portion, C5 minus C6, they destructively interfere. In fact, if they're equal, it goes to 0. So there's no more weighting on this aspect of the superposition state. This is what we mean when we say quantum interference. We're enhancing or suppressing coefficients. And in fact, this is also an example of quantum parallelism because it happens on the entire state space simultaneously. Right? So again, to emphasize, we applied one pulse. We applied it to one spin. And all of this happened at the same time. Okay, that underpins the power of a quantum computer. Okay, so how do we take advantage of this and actually implement and run algorithms? Well, it almost, at least conceptually, is the same as a classical computer. We know on a conventional computer, we have classical Boolean logic gates, and I won't read through the whole thing, but we have a NOT gate, we have an AND gate, an OR gate, with these truth tables shown here. And we know that we can form a universal set of gates, universal gate set for Boolean logic, not with just one combination, but with several different combinations. The NAND gate, the NOR gate, there are many different combinations of gates, just a handful of them, that would enable us to run any Boolean logic algorithm. It's called a universal gate set. It does require at least one 2-bit gate. Quantum is basically the same, just in the quantum mechanical realm. We have gates, and those gates represent rotations around the planet Earth. So for example, an X gate is a rotation around the x-axis. We can define one of these as x. The Y gate is a rotation around the y-axis. These are all single qubit gates. We also have a Z rotation. And we have what are called 2-qubit gates, where the state of one of the qubits determines what happens to the second qubit. But it only involves 2 qubits. One example is controlled NOT. The other is controlled phase. And with just a handful of these single and 2-qubit gates, we can form a universal gate set that runs any arbitrary quantum logic. And again, it's not unique. There are many combinations that satisfy this universality. One thing to point out is quantum gates are by definition reversible. Of course, we do have examples in classical electronics which are reversible as well. And it also requires at least one 2-qubit gate, and it has to be what's called an entangling gate. And I'll show an example in just a moment. So let's look at an example of a single qubit operation, and the analog I'm going to draw here is to the classical NOT gate. So a NOT gate, if you put in a 0, you get a 1. If you put in a 1, you get a 0. And the quantum analog to this is called the X gate, where I put in a quantum state 0 and I get a 1, or I put in a 1 and I get a 0. This is what it looks like. Now, what you're seeing here on the left is the planet Earth. The state is in blue. It starts at the North Pole and rotates to the South Pole. It's rotating around the x-axis. You can see this red arrow come in and out. And that red arrow is representing the envelope of the pulse that I'm applying to do this operation. And this pulse envelope is tuned properly so the area is exactly right to go from the North Pole to the South Pole. Now, as I'm showing it here, this is just a classical implementation because I start at the North Pole, I end at the South Pole. Those are classical states. But of course, you need not start at the North or South Pole. You could be anywhere on the surface of the planet Earth, and this gate will do exactly the same thing. It rotates by an angle pi around the x-axis. And so here I start in a superposition state, I rotate around the x-axis, I end in a superposition state, and what this x-gate does is it swaps the coefficients. Alpha 0 plus beta 1 becomes beta 0 plus alpha 1. Okay. This is just one example of the single qubit gate that we have. Okay. Let's look at a 2-qubit gate. This is the 2-qubit controlled knot. Its classical analog is the exclusive OR gate. Now, the exclusive OR gate you can think of it in this way, as having a control bit and a target bit, x and y. The truth table is here, and when the control bit x is in 0, the value of y is just passed to the output, unchanged. But when the control bit is 1, we know that the value of y should be flipped. We do a NOT gate on y, and that becomes the output. You can think of exclusive OR this way. And the quantum version is exactly the same. You have 2 qubits. One is the control qubit x, and then there's a target qubit y. This symbolism is how we represent the controlled knot. And the truth table, aside from using this funny notation called Dirac notation, which just says I'm talking about quantum mechanical stuff, it's exactly the same. The truth table is the same. And so what it means is that a rotation or an operation on qubit y, the target, depends on the state of qubit x, the control. Now, quantum mechanics follows linear algebra, and we can just figure out for ourselves how this works for a particularly interesting input state where the control qubit is 0 plus 1. It's an equal superposition. That's the control qubit x. And the target qubit is y, and it's in state 0, classical state. So let's take this one at a time. So when the control qubit is 0, we know that we shouldn't change the target qubit, so it comes down here, and you get 0x, 0y. But when the control qubit is 1, we're supposed to flip the y bit, and so that flips to 1. And now we see something very interesting here. This is called an entangling gate precisely for this reason, which is that even though when I started, I could look at something which was entirely x-like, tensor product with something that's entirely y-like, once I do this gate, I can't do that anymore. You can see that x and y are intimately tied to each other, and they're tied to each other in a way that's called quantum entanglement. I can't factor it anymore. Now, this isn't proof that it's entanglement. You'd have to look at this in different bases, but in fact, this is an entangled state called a Bell state. So this is just one example, but universal gate-based quantum computation is achievable with just a small set of these single and 2 qubit gates. This is how it works. So now let's think about an algorithm. What does it mean to write an algorithm? Of course, you'll use some sequence of these single and 2 qubit gates. And often, usually, the quantum computer will start in an equal superposition state of all of these 2 to the n aspects. And the way that I think about it is that this is an equal superposition of all the possible answers, right? I'm starting with each answer is equally likely. Because I know when I make a measurement, I'm only going to get one answer, right? We'll see that in just a moment. And so what the algorithm designer does is chooses a sequence of single qubit and 2 qubit operations. So of course, here's an example where you have a single qubit operation on qubit 3. And as we talked about, it's one pulse on 1 qubit, but it will change the coefficients of 2 to the n components simultaneously. And it does that through quantum parallelism and quantum interference, which changes the coefficients now that sit in front of this superposition state. They're no longer all equal. Sometimes we'll have couple qubit operations where the state of 1 qubit tells me what to do on the 2nd qubit. That follows quantum interference, or followed by quantum interference. It's also massively parallelized. And so by the end of the computation, the goal of the algorithm designer is to ensure that the right answer is weighted by a coefficient that's 1 or close to 1, and all of the other answers that are wrong have been suppressed to 0. And that's important, because we know when we make a measurement, we're going to project. And the probability that we get any one of these results goes as the magnitude squared of the coefficient. Remember, if you were on the equator, it was equally weighted, and it was 50-50 whether you're going to go 0 or 1. You don't want that in an algorithm. In an algorithm, you want to get the right answer 100% of the time, ideally. And so we started with an equal superposition of all possible answers. Through the course of applying gates, we suppressed all of the wrong answers. We enhanced the right one. And then when we make a measurement with high probability, that's what we get. So it's a mistaken, it's often said, and it's not really true, that quantum computers will calculate the output to all of these inputs. That's not what's happening in the quantum computer, right? That would be, a mistaken concept. What it's doing is it's suppressing all the wrong answers and enhancing the right answer so that at the end you get the right answer. But you're not going to get 2 to the n outputs. You're going to get 1 output. That's very important. It'd be great if we could do that, but we can't. Okay. So there are many algorithms that have been developed and that support this. And I just showed pictures of my colleagues here at MIT who do work on either quantum algorithms or quantum software. But, and I won't read this whole chart, but let me say that the categories of algorithm are shown here on the left. Quantum simulation is probably the, killer commercial app, I would say. Simulating materials or chemistries, for example, pharma. I also show the classical time and the quantum time here. In general, the classical time is exponential in the size of the system. The quantum time is polynomial. Factoring, of course, Peter Shor's algorithm. Sampling solutions to linear systems of equations. This is Aram Harrow and Seth Lloyd, the Harrow-Hasidim-Lloyd algorithm. Optimization, a lot of work by folks like Eddie Farhi on this one. Here, everybody's trying to optimize something, so there's clearly a commercial need for it, but the degree to which quantum computers can help us with optimization depends a lot on the optimization problem, okay? Do you need the exact solution? Is a high quality solution good enough, okay? That's why there's a question mark here. And of course, Grover's search algorithm of unsorted data, and that's a quadratic improvement, not an exponential one. So what are the ingredients for commercial quantum advantage? And I borrowed this chart from Ike. It's a fantastic chart. So first, there better be no fast classical algorithm. If we know how to do it on one of these computers, we should absolutely do it. They're fantastic. So just solve that. So first off, no fast classical algorithm for my problem. Second is, we need to know how to solve it on a quantum computer. There are many problems where there's no fast classical algorithm, and I have no idea how to do it on a quantum computer, okay? So, so you need a fast quantum algorithm. And then third, ideally you'd like it to be a useful, meaning a commercial problem. There are many examples of problems which are instructive, and we learn from them, like Deutsch-Josa, right, as an example, where you can prove that there's an exponential speedup, but it's for a problem that's not commercially relevant. And what we would like is that this overlap region is the sweet spot. We, of course, want to make this larger. And that's a charge to everyone here, especially students and postdocs, that this is what we need to do if quantum computers are going to be useful one day, is increase the overlap area. We've already alluded to it, but there are two types of quantum advantage that we have in quantum computers. And you can think of them in the following way: the size of the system or the time to solution, energy needed to run that quantum computer is proportional to a polynomial factor in the size of the system n and an exponential factor in the size of the system n. So algorithms like Grover's algorithm improve the prefactor. We call this a polynomial improvement. For example, n goes to square root of n. Okay, that's a big improvement, especially for large n. But it pales in comparison to an exponential improvement. For example, 2 to the nth power going to n cubed. N comes downstairs. That's an amazing improvement, and we don't often experience it in our everyday lives. Okay? So here's an example of exponential growth that I'd like to highlight. And what we're talking about here is I have a quantum computer, and I want to simulate that quantum computer using a conventional classical computer. How much memory would I need to store all of those coefficients in my superposition state. If you have 30 qubits, that's 2 to the 30th power. You can do that on a laptop, a beefy laptop. But just go to 50, not even twice as many, and now we need to have a supercomputer to do it, worth of memory. Go to 80 qubits, and now somehow we need all of the computers on Earth linked together and leveraging all of their memory, hopefully quickly. Maybe we need photonic interconnects or something to make this work. And then it gets ridiculous. Like double that to 160 qubits, and now we would need all of the silicon atoms on Earth, and every silicon atom is representing 1 bit of the memory. And now go to 300 qubits, just 10 times where we started, and now you would need all the atoms in the known universe working together as memory elements for this fictitious computer. Okay. This doesn't tell us how to build a quantum computer, but it does give us a concept of what exponential scaling means. Okay. So it sounds great. Why don't we have quantum computers right now? Or why don't we have large fault-tolerant quantum computers right now? And it comes down to these 2 times. One is coherence time, and the other is the gate time. So the coherence time is basically the qubit's lifetime. How long does it remain quantum mechanical? Now, I'm including here coherence due to noise, but it can also be due to control errors, our classical control. We start out with a computer, quantum computer, in a known state of all those qubits, call it psi, and as soon as we start trying to run our algorithm, it starts interacting with its environment. There are temperature fluctuations, magnetic field fluctuations. The subway just left Kendall Station, and you can see it on your qubits. Everything, they're very sensitive. And over time, you can think of this state of my computer blurring, and eventually it's lost. What does that mean? Well, the qubits are still there, but in some notion of a high-dimensional state space, I was trying to go from this starting point to this end point, which is the answer to my problem. And as I'm marching along with my gate operations to get there, the noise is actually taking me somewhere else. And I don't know where I went at the end. It's blurry because I don't know everything that the noise is doing. Okay. The time frame over which this blurring happens is called the coherence time. The second time we care about is the gate time. How long does it take me to do an operation? A typical time. And the figure of merit then is how many operations can I do within this lifetime that I have? Okay, more operations being better. Now, one caveat here is that people often trumpet, my qubit has a coherence time of 10 hours. Okay, great, that's not a bad thing. But what's important is how many operations can you do in that 10 hours? And to give an example, a little bit of a ridiculous example, think of a neutrino. You might think a neutrino is a perfect qubit because it lasts forever. But it's not, because I can't operate. I can't even detect it, right? And so it's not just having long coherence times. Often the technologies that have long coherence times, they do it or have that long coherence time because they don't listen to the noise. If they don't listen to the noise, they don't listen to me either when I'm trying to run the algorithm. And it turns out, as we'll see on the next chart, these technologies, almost independent of their coherence times, have roughly the same number of operations that they can do within that time. Okay, so why don't we look at that chart? So what we have here is the number of operations before an error. And on this horizontal axis, we have the gate speed, think of that as the clock speed. Now, the number of operations before an error, you might think of as the gate fidelity. So for a given gate, what percentage of the time does it work? So if I have 1 error in 100, that's 99%, 1 error in 1,000, that's 99.9%, et cetera. And of course, you want to be fast and high fidelity. And so now we can take a look at different competing platforms. So one is trapped ions, which Ike works on, along with John Chiaverini at Lincoln and Rajiv Ram here at MIT. And you can see that trapped ions have very high fidelity single qubit gates. They're improving the 2-qubit gate. And they're trying to get faster to get into the upper right corner. I work on superconducting qubits along with Kevin O'Brien, who'll speak this afternoon, Terry Orlando, Jamie Kerman out at Lincoln. And we are pretty fast, and we're trying to get higher fidelity. And so in some sense, we're both equally far from this upper right corner. Neutral atoms have really started to shine in the last couple years. This is where they are, and some of our colleagues here, Vlada and Wolfgang and Martin, working on this technology. Nitrogen vacancy centers, or just generally speaking, defects in silicon or other substrates, they can be used for computing. They really shine as quantum sensors, magnetic field sensors, for example. And then my own group is starting to work also on silicon quantum dots, which probably is the closest to a silicon transistor of the qubit technologies. Now, these circles that just appeared here are giving us an indication of how fast we would actually be able to run a computer in practice, because we need to do error correction if we're going to do sustained computations over long periods of time. And so for the superconducting qubits, it's about a megahertz. For some of the natural atomic systems, it's about a kilohertz. And everybody's going to try to get faster. It matters. It really matters. Because all else being equal, an important caveat, but all else being equal, if it takes me a day to run an algorithm on a superconducting quantum computer at a megahertz, it's going to take me 1,000 days on something that runs 1,000 times slower. And even though both technologies didn't take the age of the universe, it's an exponential speed up over a classical computer, it still matters how long it's going to take, because I don't want to wait 3 years for the answer. I'd like the answer within a day. And so the speed still matters in quantum computers. Okay, lots of research going on. I would say there's no clear winner. And also, just like with conventional technology, classical computing technology, it'll evolve over time. Right? We started with bipolar junction transistors. We later had emitter-coupled logic. And we worked our way eventually to be at CMOS. It didn't, in fact, we started with vacuum tubes before that. The technology will evolve and change over time. Okay. Let me check the time. I'm probably speaking a little too slowly. Yeah, so let me talk a little bit about superconducting qubits. These are artificial atoms. We build them from circuit elements, like inductors and capacitors. This, in fact, is a quantum circuit element. You probably recognize it. It's the LC oscillator. And one property of an LC oscillator is that it's harmonic, which means that its potential is quadratic. And at room temperature, you don't see these discrete energy levels because they're separated by the resonance frequency, 1 over square root of LC. But if you cool it down to a low enough temperature where the energy scale of the temperature, kT, is much less than the energy scale h bar omega, which is the separation here, you will see discretized energy levels for this circuit. I think that's amazing as an electrical engineer. It's a great circuit. It is quantum mechanical, but it has this one issue, is that if I want to make a qubit from it with a 0 and a 1, I could do that, but when I drive 0 to 1, I also drive 1 to 2 because it's the same frequency, and 2 to 3 it's the same frequency. And very quickly, I leave my 0-1 subspace. That's a problem. So we have to do something to make this circuit anharmonic. And what we do is we add a Josephson junction. Now, for our purposes here, a Josephson junction is a nonlinear inductor. Okay? Brian Josephson gave us the current and voltage relationship through this device. It's 2 superconducting leads separated by a thin tunneling barrier. But when you combine it in the usual way to define inductance, you find that the inductance value of this circuit element depends on how much current goes through it. That's the definition of a nonlinear inductor. Its value changes as the current changes. You could even integrate current and voltage in time to get the energy. And what you find is the energy now is shaped like a cosine potential rather than this parabolic potential. And so if I made a LC circuit, but I made it with a nonlinear inductor, the potential profile now shown in blue, the cosine, differs from a harmonic potential. It's an anharmonic potential. And what that translates to is the 0-1 frequency is now different than the 1-2 frequency. And that's what I need to stay in the 0-1 subspace. I drive that resonantly, I'm off resonance with the other transition. Okay. This circuit element, in fact, is a qubit that's used today quite widely. It's called the transmon. It's used at IBM. In different forms, it's used at Google. You could think of this as the hydrogen atom for superconducting qubits. Okay. Now, we have to cool them down to very low temperatures, as I mentioned. And how low? Well, typically these qubits will have a frequency that's around a few gigahertz, say 5 gigahertz. That's a thermal energy of 250 millikelvin if you equate kT and h bar omega. You want to be much colder than this. You don't want the thermal environment to excite it. So we want to operate, say, 10 times colder, around 20 millikelvin. And that's great because these refrigerators, called dilution refrigerators, get us down to that temperature. Now, 40, 50 years ago, this was somebody's PhD project, but today they're commercially available. You just buy them. We have 12 in our lab the Engineering Quantum Systems Lab, and many faculty at MIT have refrigerators like this. And you can see in here everything, this is about half a meter across, half a meter down, and it's all at 20 millikelvin, right? Coaxes, switches, filters, attenuators. Over time, we've learned what works at these temperatures, and of course, that's what we use. Superconducting qubits are fabricated, meaning that we manufacture them on silicon. This is a 200 millimeter silicon wafer, lots of qubits on here. If we zoom in on one of the circuits, you can see these 5 plus signs in a row. Those are 5 superconducting qubits. The plus is actually the capacitor. So rather than using parallel plate, we just use something that's lateral. And why a plus? Well, we envision not just having a line of them, but we want to go north, south, east, and west. So that's how we can connect to neighboring qubits. If we zoom in further, so that's the capacitor to ground. If we zoom in further, this little piece right here, this loop, is called a squid. It's actually a Josephson junction, 2 Josephson junctions in a loop, with a property that if we put a magnetic field through that loop, we can actually tune the qubit's frequency. That's useful. So the qubit's in the fridge, I'd like to change its frequency. How do I do that? I just apply a little bit of current to an antenna and I can change the frequency. And then the smallest feature size, about 100 nanometers, is the Josephson junction itself. So we're not pushing lithography here. If anything, these are very, very large devices. Now, how do we control it? We control it with microwave IQ mixing. And so this planet Earth over here, you can see the qubit state in blue going around the Earth. And it's going around based on these pulses in red. And I apologize, the blue and the red on the left are not the same as the blue and the red on the right. The blue and the red on the right is a result of in-phase and quadrature mixing. So the I port of a mixer, we're going to say, is blue. The Q port is red. And your local oscillator going into this mixer gets multiplied by the I or the Q pulse. And you just decide which pulse you want to send. Am I sending it to I or am I sending it to Q? And the mixer multiplies them together and you get this pulse out. And again, if we tune the area of that pulse just right, we can get either a pi pulse or a pi over 2 pulse. The difference between I and Q is a phase shift of 90 degrees, and that tells me whether I'm going to apply that pulse along the x-axis or the y-axis of the Bloch sphere. So just standard IQ mixing is how we can control these circuits. So using this in our group, we have more than 4 nines of single qubit fidelity and more than 3 nines of 2 qubit fidelity. And the higher the fidelity, the better, as we remembered. Now, just to give a flavor of the research, I think Kevin will likely talk more about this in the afternoon, is that it involves a lot. And that's actually why it's taken a long time to develop quantum computers in general, is you need to develop the materials, you need to analyze the materials, design the circuit, model it, build your circuit, fabricate it, maybe it involves some bump bonding, some process monitoring. Then you have to cool it down in one of these refrigerators, it takes a lot of equipment, and then you get some result out, and then you validate or refute the hypothesis you had, and then you iterate this many, many times. Okay. So we have this today, but starting out, you know, this was basically a black box, and people had to figure it out. But things are accelerating quite rapidly in this field over the last 5 years, precisely because we can now efficiently do this optimization. If we look at the coherence over the last, I would say, 20 or 30 years, first qubit was about a nanosecond. And today, our qubits are actually at a millisecond and more. And so that 6+ orders of magnitude improvement is part of the reasons why many companies are pursuing superconducting qubits. They've improved dramatically over the past many, many years. This is what quantum computers look like today. IBM's Osprey here in the lower left has 433, I think, something like that, qubits. This is Google's Willow chip, which just had the very large announcement about the first time a quantum error correcting code was beyond threshold. That's a big deal. This one in the middle is a neutral atom quantum computer called Aquila from QEra, a startup company started by folks at Harvard and MIT. This is Quantinuum's H1 chip. This is a trapped ion chip in a racetrack style. This is D-Wave's quantum annealer. It's also superconducting, different type of quantum computing. We won't get into it today. This, of course, is not a quantum computer. You'll recognize this as the Wright Flyer. It wasn't the first time humankind had flown. That's actually a misconception. We had hot air balloons. We had gliders, people jumping off cliffs with wings. But this was the first time that it all came together. There's a person on board, steering, self-propelled. It took off. It landed. If you read the history of this, they did 6 flights that weekend, crashed once or twice. They had to go back and fix it. I put it here because it reminds me of where we are today in quantum computing. My students will say that things crash and they have to fix it every weekend, probably. But the point is that when we saw this, particularly in hindsight, when we see this event, we know that commercial aviation will come. Clearly, it's not ready yet. But we know that it's matured to a point where we can envision commercial aviation. And I think, by analogy, that the quantum computing systems that we see today are likely equally immature, but have risen to the point where we can see that commercial quantum computing will come. And to realize that, we need to engineer the systems that are robust, reproducible, and extensible. So this will be my last slide because I'm running out of time. The grand challenge today is quantum error correction. So these computers can operate for a certain amount of time, but eventually decoherence takes over and we lose our quantum coherence. But that's not the end of the game, fortunately. If we look at the physical qubits that we have today, their error rates are 1 in 100 to, say, 1 in 10,000. And groups around the world worked really hard to get the quality to that point. That's pretty amazing, right? That out of 10,000 gates, only 1 failed. But you could ask, what do I need for practical, commercial computing? You need something in the billion to trillion range. I need to run 1 billion or 1 trillion operations in order to do something that's commercially useful. And there's a big gap, a giant chasm between these 2 points. And how are we going to make it up? By the way, the transistor I mentioned before, almost never fails. And maybe one day we'll get to that point with quantum computing. Fortunately, we don't have to get there to see the first commercial advantage. So the way that we're going to do it is called quantum error correction. And you can think of it as forming a team of qubits. So rather than trying to encode information in a single qubit, we're going to form a team. Here it's a 3 by 3 array, so 9 qubits that are yellow. 9 physical qubits together forms a team, and that team is going to, ideally, outperform the individuals there. Now, you also see some blue qubits here, and the blue qubits are like referees or checkers. They're going to look at the neighbors, and they're going to say, oh, foul, foul. They're going to let us know so we can go back and correct. Now, when we do that, we call this thing a logical qubit. And when we do that, the logical error, the error rate of the logical qubit, in fact, has a prefactor that makes it worse. Okay, obviously. If we form a team of qubits, we need to do more work, more gates, more operations, so that's a penalty. But in implementing this protocol, we do get an exponential advantage, and it's exponential in the size of our logical qubit. So the way that I think about this intuitively is imagine a room of kindergartners. Heartwarming, 20 or 30 kindergartners. Everybody running around, screaming, having a good time, okay? Those were the qubits of 10, 15 years ago, all right? If you add more kindergartners to that class, they're just going to get worse. It's not going to get better, okay? But somewhere along our educational trajectory, we get to a point where if 2 people form a team, they outperform any individual, or 3 people, or 10 people, or 20 people. There's a threshold that we cross in our education, and when we cross that threshold, adding more people to a team makes the performance of the team better and better and better. And in fact, we have companies that have hundreds of thousands of people working together, and this penalty here is, okay, now I need an HR department to keep it all straight, but the benefit of putting all those people together outperforms not doing it. Okay, so that's the concept of error correction. And it's very powerful. What I'm showing here is the logical error per cycle. On the vertical axis, the horizontal axis is the error rate of the physical qubits. And you can see they're quite different. We're talking about 0.1% error rate on the physical qubits, 1 in 1,000. But on this axis, we're getting down to 1 in 1,000,000 or more. And the way that we do it is that we have to be on this side of the threshold. The qubits, they can't be kindergartners. They have to be more mature than that. And the more mature they are, the bigger advantage we get by aggregating more and more qubits together into a logical qubit. And every time I increase the size of this, distance 3, distance 5, distance 7, I go down by the same factor. That's this exponential improvement. And this is what Google showed, or announced, I should say, in December. Full disclosure, I work with them and was on this paper with them. But what they showed is that in red, they have the distance 3 code. In blue, they have the distance 5 code. And in dark, I should say teal, and then in dark blue, they have the distance 7 code. And every time they increased the size of the team, the error rate went down by more than a factor 2. Now, of course, we want to do better than that. We'd love it to be a factor 10. But it works, and this is the first time that this scaling with the size of the logical qubit had been shown in any technology. This is the side of the line we want to be on, because we want to build quantum computers that have millions and millions of qubits. And as we add more and more qubits, the error rate better go down. If it doesn't, then we're still in the kindergarten era. But we're not. This was the first time it was shown. So they demonstrated improved performance going from a distance 3 to a distance 7. There have been many demonstrations of quantum error correction with other modalities, encoding logical qubits, showing that they can turn the crank. But this was the first time that it actually worked. Okay. And so I think I'm going to stop there in the interest of time. I thank you for your attention, and we may be able to take a quick question or two, but then I'm going to also invite Ike up to switch over to the next talk. Thank you.
It was a very good introduction. There were a few things that I was confused about.
Okay.
Two questions. What is the relation of a coherence time and the error rate? If the coherence time goes up, does the error rate go down?
Generally speaking, yes, for a given technology, because what matters is that, how many operations can I do within that coherence time? So if my operation time is always the same, and I make the coherence time longer, then I can do more operations on average before things fall apart.
The second question is, in your big diagram, you showed that the uptime was much greater if you only had 1 gate per qubit versus 2 gates per qubit. Why does adding gates reduce the amount of time by so much? And what is the advantage of having more gates per qubit?
Sorry, can you say that? I'm trying to remember which slide you're thinking of.
Like 10 to the 5th, it was the big slide of performance of...
Comparing different modalities?
Yeah.
That one? Okay. And what was the question again?
You had 1 qubit, 1 gate per qubit and 2 gates per qubit, and you had 2 different numbers.
Oh, I see. Yes. So thank you. I did not mention that. Yeah. So to do universal quantum computation, you need single qubit gates and 2 qubit gates, meaning an operation that I apply to only 1 qubit at a time, or operations that I apply to 2 qubits at a time. And so if we want to compare these different technologies, we can't just look at the single qubit gate, although people often will say, hey, my single qubit gate is so good. Okay, but you can't do universal quantum computation with that. What's your 2 qubit gate fidelity? That's also important. And that's why I had those 2 numbers on there.
But the uptime for the 2 qubit gate was much...
It tends to be harder. That's right. It tends to be lower fidelity precisely because it's more complicated. There are 2 qubits that I'm trying to operate in tandem. And as a result, it generally is slower, although not always, and it generally has lower fidelity. Yeah. Good. And I'll be around. I'm happy to talk more offline or at the lunch today. I don't want to eat into Ike's time. So